Hello, I hope that everyone had a great weekend. Today we're going to start with chapter 9, section 6, and then we will continue to take notes until Thursday. And on Friday, we will have another Zoom conference to go over any questions and discuss the material that we went over this week. So let's get started. 9.6 is going to be on page 262. And the title of this chapter is The Effect of Pressure on Solubility Henry's Law. So pressure has virtually no effect on the solubility of a solid or a liquid, but it has a strong effect on the solubility of gas. So the first thing that we need to know is pressure impacts the solubility of gas. According to Henry's law, the solubility or concentration of a gas in a liquid is directly proportional to the partial pressure of the gas over the liquid. Recall from section 8.10 that each gas in a mixture exerts a partial pressure independent of other gases present. If the partial pressure of the gas doubles, solubility doubles. If the gas pressure is halved, solubility is halved. So the next thing that we are going to define is going to be Henry's law. So this states that the solubility or concentration of a gas is directly proportional to the partial pressure of the gas if the temperature is constant. So the equation for this is going to be C over P gas equals K at a constant temperature. So C is going to be equal to concentration, P gas is the pressure of a gas So now if you look at figure 9.3 on page 263, it says there's a picture and it says Henry's law, the solubility of a gas is directly proportional to its partial pressure. So we want to note that it's directly proportional to its partial pressure. An increase in pressure causes more gas molecules to enter the solution until equilibrium is restored between the dissolved and undissolved solution. So Henry's law can be explained using Le Chatelier's principle, which states that when a system at equilibrium is placed under stress, the equilibrium shifts to relieve that stress. In the case of a saturated solution of gas in a liquid at equilibrium exists whereby gas molecules enter and leave the solution at the same rate. When the system is stressed by increasing the pressure of the gas, more gas molecules go into the solution to relieve the increase. Conversely, when the pressure of the gas is decreased, more gas molecules come out of the solution to relieve that decrease. So how that can be written is going to be gas plus solvent solution. So this is just stating that the pressure can shift so that the solution will become at equilibrium. So for example, an example of this is the CO2 gas dissolved under pressure comes out of a solution when the bottle is opened and the pressure drops. So as an example of Henry's law in action, think about fizzing that occurs when you open a bottle of a soft drink or champagne. The bottle is sealed under greater than 1 atmosphere of CO2 pressure, causing some of the CO2 to dissolve. When the bottle is opened, however, CO2 pressure drops and gas comes fizzing out of the solution. Writing Henry's law in the form P gas equals concentration divided by K shows that partial pressure can be used to express the concentration of a gas in a solution, a practice especially common in health-related sciences. Table 9.4 gives us some typical values and illustrates the convenience of having the same unit of concentration of gas in both air and blood. So this is the table I'm going to want you guys to know as well, and we'll write these down together. It's going to be table 9.4 on page 263, and this is going to be partial pressures and normal gas concentrations in body fluid. So this is the sample. We're going to have inspired air, so air you breathe in, alveolar air, when it's in your lungs, expired air, when it leaves your lungs, arterial blood, so when it's in your arteries, venous blood, when it's in your veins, and peripheral tissues, so when it goes to other tissues. The pressure of N2 is going to be 597, 573, 569, 573, 573, and 573. And then the pressure of O2 is going to be 159, 100, 116, 95, 40, and 40. And the pressure of CO2 is going to be 0.3, 40, 28, 40, 45, and 45. And the pressure of H2O is going to be 3.7, 47, and 47. So compare the oxygen partial pressures in saturated alveolar air in the lungs, in arterial blood, for instance. The values are much the same because the gases dissolved in blood come to equilibrium with the same gases in the lungs. If partial pressure of a gas over a solution changes while the temperature is constant, the new solubility of the gas can be found easily because C over P is a constant value at constant temperature. Henry's law can be restated to show the variable changes in how the variable changes in other changes. So how we're going to write that equation is going to be C1 over P1 equals C2 over P2, where C is going to be, this is also equal to K. So it's going to be concentration. P is pressure. K is the constant. So we're going to do a worked example, which is going to be on page 264. And this is going to be example 9.3. So to do this problem, I'm going to write it out for us really quickly. It says at a partial pressure of oxygen in the atmosphere of 159 millimeters of mercury, the solubility of oxygen in blood is 0.44 grams per 100 milliliters. So what is the solubility of oxygen in blood at 11,000 feet, where the partial pressure of O2 is 56 millimeters of mercury. So the equation that we're going to use is going to be C1 over P1 equals C2 over P2. So we know P1 is 159 millimeters of mercury. We know C1 is 0.44 grams per 100 milliliters. We know P2 is 56 millimeters of mercury. So we can switch this equation to solve for C2, and C2 becomes equal to C1 P2 over P1. So if we plug in the numbers, it's going to be 0.44 grams over 100 milliliters. Make sure you use your parentheses. 56 millimeters of mercury and 159 millimeters of mercury. So the millimeters of mercury cancel out, and you are left, when you do the math, with 0.15 grams per 100 milliliters. So that will be the correct answer for that one. So for homework, I want you to do 9.6, 9.7 on page 264.